Assalamu alaikum once again. We're back with another video lesson. If you remember in the previous lesson, we talked about simple harmonic motion. And of course, before that, we talked about periodic motion. Do you remember what was periodic motion? We said it is this repetitive back and forth movement. Of course, that is what is called periodic motion, yes? And of course, when something kind of like moves back and forth, or when something happens again, let's say periodically, that is what is called periodic motion, okay? All right, or you can say something, this repetitive back and forth movement about the equilibrium, that is also can be considered periodic. Okay, and then after that, we talked about simple harmonic motion. We said simple harmonic motion is this repetitive motion, you can say, or if I can take you back to the definition, of course, we said simple harmonic motion where the motion of the object or this vibration where the restoring force is directly proportional to the displacement, of course, and then there was another condition there. We said this back and forth movement has to be on a straight line around or about the equilibrium position there. Okay, so, and then of course, we did explain like what happens when a mass spring is stretched, of course, what happens to the maximum, what happens at the equilibrium position, what happens when it is, for example, at the other end, whether if it is stretched or compressed in this case. We said when it is stretched, at the end, for example, or maximum displacement, the restoring force, don't forget, it is maximum, the displacement is maximum. The, let me redraw this one just to make sure that you remember all this. We said, we'll just draw one spring here, perhaps, okay? So we said if this is a spring here, at maximum displacement here, where x is maximum, remember, if x is maximum, the restoring force, elastic force is also maximum. If that is the case, acceleration is maximum because these two are directly proportional to one another. And if that is the case, elastic potential energy, by the way, what is the type of energy here? Of course it is elastic, you do know this one. It is also going to be maximum. But if there's no motion here, that means the velocity is going to be zero, kinetic energy is going to be zero, and of course the momentum will also be zero. What happens when you let it go? For example, it goes back to the equilibrium position, yeah? If it is at equilibrium position there, let's say x is zero. If x is zero, that means the force, elastic force, the restoring force will be zero, the acceleration will be zero, but then all this elastic potential energy will change to kinetic energy, which means that the velocity in this case will be maximum at restoring force here. So we can say F is zero, acceleration is zero, elastic potential energy is zero, and then, but the things that will be maximum was velocity will be maximum, kinetic energy will be maximum because all this potential has converted to kinetic energy, so it's going to be maximum, and of course the momentum also, because it is equal to mass times velocity, will also be maximum at these points here. Okay, but as it passed through the equilibrium, of course, these values will start to decrease, and of course, these will increase right after here until they become maximum. But one thing that always remains constant, which was one of the past exam questions, is the mechanical energy. Remember, at a point here, all the energy, or the energy that there is, solely is elastic potential energy. But at a point here, all the elastic potential energy is converted to kinetic energy. In another word, that means potential and kinetic energy, they always interchange, yeah? Increase or decrease, they vary. But one thing that as a total remains always the same or constant is the mechanical energy, which is the total kinetic and elastic potential energy in this case. Okay, so we have one question here. Do you remember the Hooke's law or the equation? Was that F elastic or elastic force equal to negative K times X, okay? X was the displacement, K was the spring constant, and of course F was the elastic force, you can say. And of course we said we can also call it restoring force as well. Okay, so what do we have in this case here? We have an example that says, if a mass of 0.5 or 5, yeah, is attached. Let's move this one here. Let's, not this one. I think I need to move this one up a little. Yes, okay. Let's make it white. Take a look here. We said in order to do this correctly, always consider x to be negative. So we have, if a mass of 0.5 5 kilogram attached to a vertical spring. Remember, sometimes springs can be put like this. Okay, so for example, this is horizontal, or they could be something like this, yeah? So this is vertical, this is horizontal. But remember this, when it is vertical, always this mass that is given, you'll have to multiply by what? You'll have to multiply by gravitational acceleration in order to get what? To get Fg here, because Fg is what is pulling the spring downward here. So don't forget. If mass is given and you need the force, always multiply by g, gravitational acceleration, which is 9.81, then of course you will get Fg here. You can also call it the weight of the object as well, which in this case kind of like works as the force that pulls the spring, okay, or extends the spring here. So we have a mass. What is the mass? The mass is 0.55 kilogram, okay? To vertical, stretch the springs 2 centimeters. So remember, we said we'll consider x to be negative always, okay? But what is given here is 2 centimeters, guys, okay? Can we use centimeters? No, you have to convert centimeter into meter. So 2 centimeters divided by 100, you can say 0.02 meter in this case. Don't forget, we'll use negative. That is because the stretch, the displacement is opposite to the stretching force here. From its equilibrium position, that is the extension or the displacement, what is the spring constant? What is what? The spring constant, or in another word, find K. So how do you find K? We do know the equation, yeah? Hooke's law. Hooke's law says what? What does it say? It says F equal to, let's use a different color. Okay, so it says F elastic, of course, right? Equal to what? Equal to negative Kx in here. Remember, we said this negative, let me write it better so you don't get confused. F elastic equal to negative Kx. But what provides the force that is stretching the spring here? Of course, that is the gravitational force. So, of course, we can say F elastic here equal to Fg in here. Or in another word, you can even ignore this E here. You could just say F equals to negative Kx. We don't care about what force is stretching the spring here, but as you can tell here, the mass is stretching, yeah? But remember, not only the mass with the gravitational acceleration, that is going to be the weight. So in this case, the force that provides or stretches the spring, that is going to be mg, okay? Or you can use this to here, Fg, that will be mg, Fe, that is negative Kx, or I can just use mg, which is equal to negative Kx in this case, yeah? We're trying to find K in here, yeah? So how do you find K? You can rearrange the equation and you can move the x and the negative to the other side. So we can, by the way, we said this x is negative, so don't forget. So we can say K equals to mg, and of course negative x, yeah? But then the x is also, or itself is negative, so perhaps I need more space to do this one. Or perhaps I should have moved this up a little. Okay. So I'll try to bring it back in here. So K now equals to what? Equals to the mass, which is 0.55 times gravitational acceleration. You do know the value, which is 9.81. Correct, yes? And then this negative, remember, this negative is from the equation multiplied by x, but x is already a negative, yeah? Which is negative 0.02 meter. Negative becomes positive, and of course now, what will be the answer? You do the calculation and then you will see that the answer will be, let's see if we can take a look. The answer will be 270 Newton. Let's see if we can take this one back. All right, yes, so we can say the answer here will be 200, let's erase this one as well, 200 what? 270 Newton per meter. Why? Because that is the unit for the spring constant. So remember this, it is pretty simple if you don't confuse yourself, and that's it. Let's do more until you fully understand how it is done. We have another question here. It says, a slingshot consists of a light leather. When we say light leather, that means ignore the mass of the leather. whenever something is light, we generally are ignoring the mass of that object. Leather cup attached between two rubber bands. If it takes a force of 32 Newton to stretch a band 1.2 centimeter, again we have centimeter, we're not using centimeter, you will have to convert this to meter. What is the equivalent spring constant of the two rubber bands in here? Okay, so once again, remember, in order we said it that in order to do this, we'll consider x, okay, always to be negative. This will do the job, okay? Let's move this one down a little. Okay, so take a look. It says a slingshot consists of this. So what is the force? If it takes a force of 30, so we have elastic force here, or you can say a force that you need to, let's say, to pull the shot. So in order of saying elastic, I'll just say the force in this case, which in this case, it doesn't make a lot of difference in here. So F for this one, which is 32, what is it? 32 newtons. 32 newtons. In terms of the value, it doesn't make any difference. Okay, to stretch the band, which is 1.2 centimeters. So we can say x, the displacement is, remember, we always use negative. So here's a negative 1.2 centimeter. Convert 1.2 centimeter or 1.2 divide by 100. Of course, you will get 0.01 meter in this case, because we've just converted centimeter to meter. And then find what? What is the equivalent spring constant? So find K. So once again, all right, now F elastic equal to what? Equal to negative Kx. We want K, so again, K equals to F over X, yeah? But don't forget, there is a negative as well. And then F is 32. F is 32 Newton, and then divided by negative, remember, X will be negative regardless to the negative of the sign in this case, which is going to be negative. X is negative as well, so it's going to be negative 0.012. And of course, use a calculator. Use a calculator and tell us what is the answer there. So K will equal to this much Newton meter, okay? And of course, you can see that the answer will be 2.7 times 10 to the power 3 newtons there. So you can see here, there is one negative for the equation, there is one negative for the x, then we'll get a positive value for K. Remember, there's one thing you need to know, that K, the spring constant, can never be negative, okay? Because it determines the stiffness of the spring. Now take a look. This one says, how much force is required to pull a leather cup of question 1 a distance of 3 centimeter from the equilibrium? We found spring constant, yeah? So we do have the spring constant. Let's use red. So we did find, okay, we did find K, which was 2.7 times 10 to the power 3. Now here we have the extension, or the displacement x, which is going to be negative 3 centimeter, convert to meter, 0.03 meter. And then if you have K and X, or the displacement, can you find the force? Yes, you can do that using the equation of Hooke's law, and that is how it is done. Okay, now take a look at this one here. A stretched or compressed, right, let's use this one more time. Okay. Now it says what? A stretched or compressed spring, of course, they has, if it is both, let's say, elastic material, of course, then stretched or compressed spring has elastic potential energy. Remember, when we have springs, those springs, of course, will have elastic potential energy in them, yeah? So don't forget, not only a spring, let's say, it could be an arrow, it could be, let's say a bowstring and not an arrow, bowstring and the bow, let's say itself, yeah? Because once you're trying to stretch the string there, of course, the string is elastic, yeah? So once you're stretching this, of course, you're converting mechanical energy in your hand into, let's say, the elastic potential energy inside the string. So once you let it go, this elastic potential, of course, will convert to kinetic energy as well, and part of it will go into the bowstring as well. But you can say most of the part, or most of that energy, will go to the arrow, and of course then the arrow will be flying in the air. So we can say this elastic potential energy will be converted to kinetic energy. If we assume that all the energy or elastic potential energy converts to the arrow, then of course we can say the energy is conserved, and then all the elastic potential energy will be conserved into kinetic energy in that case. Okay, so remember this. It says, consider an archer shooting an arrow from a bow, bending the bow by pulling back the bowstring, which is analogous to stretching a spring. So if we disregard friction and air resistance, of course, or internal energy, once the bowstring has been pulled back, the bow stores what type of energy? Elastic potential energy. Why? Because it is being stretched, of course. And then after that, after it is, let's say, the bow, the string are now at rest. If it is at rest, there's no motion, there's no kinetic energy. The kinetic energy of the system will be zero. But what happens when you let the string go? Of course, then you can say all this kinetic or elastic potential energy will be converted to kinetic energy. And of course, part of it will go to the bowstring as well. But we can say one thing that is always conserved, the mechanical energy of the system is solely elastic once it is not moving. You just stretch, and then what happens when you let it go? Of course, when the string is released, most of this bow's elastic potential energy is converted into kinetic energy of the arrow, which then, let's say the rest of the elastic potential energy is converted to elastic or kinetic potential energy. What potential energy? No, that's a different one. All right, so converted to kinetic energy of the bow and the bowstring. The mechanical energy of the system is always conserved. Don't forget this. Okay, it's solely once, if we assume there's no friction or air resistance, and once the bow is released, the energy of the system is going to be solely kinetic energy, because there's no elastic anymore. The bow goes back to equilibrium position, the string. Because mechanical energy must be conserved, so the total kinetic energy of the bow, the arrow, and the bowstring is equal to the elastic potential energy, which is originally or initially stored in the bow. And of course, we have something else, which is also, you might see this inside store of shock absorbers here. Take a look. You see car suspensions and springs, yeah? And then, or something different here, like before using car suspension. Once you, for example, you're driving a car very fast, and of course you encounter a bump. So once you pass or walk through the bump, of course, the tires or the car would normally, for example, move a little bit up, yeah? Because there is bumpy, so it goes up a little bit. If, in this case, your car will be flying in the air for a second, let's say. But you know that this is very risky, very dangerous. So we want something to, like to push or to help the tires to go back on the floor, on the road, so that you can have control on the steering wheel, and then you can drive your car safely. But you see, so springs will be best, because once you go on a bump, of course, it moves up, and then after that, it kind of like pushes on the tire back on the road, so you can have, or the tires will be attached to the will be back to on the road. But there is one problem. You do know that springs will move back and forth, yeah? We don't want you to drive your car and at the same time bounce up and down, yeah? It might be fun, but very dangerous, yeah? So, how do we overcome this problem? Of course, we can overcome this problem by using shock absorbers. And how do they do that? Of course, shock absorbers are basically, you can say, devices, or you can say tools that are fluid-filled devices, or tools, you can say, contain a fluid. Of course, this fluid allows this vibration or back and up and down movement, bouncing up and down movement, to be less, or reduces that, yeah? That is what is called shock absorber. So instead of your car moving or bouncing up and down, of course, after, for example, it encounters the bumps, maybe just one up and down, and that's it. You go back to normal, and that is the purpose of shock absorbers. So what they do is they damp the oscillation. They prevent the object from oscillating, let's say, too many times. Perhaps the like new shock absorbers are specifically designed so that they only vibrate, let's say, one cycle, and that's it. They stop the oscillation completely so that you can have control over the car without being at risk of losing the control. So of course, these are the springs. Okay, we have two types of springs. You can have either this, of course, a coil spring, or you could have this one, a leaf spring. That is for heavy duty, let's say. And shock absorbers are this and this one, of course. Yeah, these are tools that are filled with fluid, and of course they absorb the shock, or they absorb this up and down there so that you don't continuously move up and down while you're driving your car. So these will be the definition, of course. So their job is to eliminate vibration. Now we have something else called simple pendulum. Yes? Now what is a simple pendulum? We did talk about mass spring system, yeah? Mass spring system where a mass is attached to a spring, and once pulled, or let's say once stretched or compressed, it can move back and forth. If the system is ideal, it can move back and forth continuously forever. But we know that there's no such system. So after some vibration or after some time, it goes or stops oscillating. That's one. And then we said the spring could be horizontal or it could be moving up and down. That is, depends on the case or the situation there. And then, but now we have a simple pendulum. What is simple pendulum? You can say simple pendulum, it is a mass that is attached on a string, let's say, or on a rod that swings back and forth. Okay, so of course there is simple harmonic motion, you can say, if the angle is not that much, and of course back and forth under gravity's influence, showing periodic motion. All right, so remember, how do we define? You don't have to memorize the definition. Remember, just know what is simple pendulum. It is normally a mass attached to a string, or sometimes could be a rod. This string or this mass will be moving back and forth. All right, this back and forth, of course, that is what makes it simple harmonic motion. Later on we'll talk about it, yeah? Or periodic would be most, yeah? Then when do we call it simple harmonic motion? Of course, we'll get into this part as well. But why does it move back and forth? It is because of the influence. It is because of the gravitational acceleration. Okay, in simple pendulum, we assume that the mass of the bob is what? We assume that the mass of the bob is concentrated at a point. So if we use a bob, of course, that would be a circular mass or a sphere. We could use different shapes, of course, but in order to eliminate or reduce air resistance, of course, we can use spherical shapes would be best in this case. And of course, we consider that the mass is concentrated at the center. And of course, the mass of the spring will be negligible. The effect of friction and air resistance is disregarded. So we can say we have an ideal situation where the pendulum can swing back and forth. And of course, if there's no resistance or air friction, then the pendulum can swing back and forth forever. The effect of friction and air resistance, ignored, disregarded, yeah? And then, but in a physical pendulum, the mass distribution and the factors mentioned will be taken into account or consideration. The restoring force in a pendulum is a component of what? Of the bob's weight. What do we mean by this? All right, now let's see if we can get this. Okay, take a look here. You do know what is a pendulum. Take a look, here's a pendulum. Okay, so we have, let's say this is the string, and there is a mass that is attached to the string. You can call this mass bob, okay? So this mass will be moving or oscillating back and forth. Will be moving back and forth, assuming that this is the equilibrium position where x, you can call it 0 here at this point. And of course, at a point here, at some time it will be here. If it is at this point, you can call x to be maximum here, okay? And if that is the case, the restoring force, of course, here is going to be maximum as well. all right, and the acceleration will also be maximum. But what about the type of energy here? Remember, the energy is going to be gravitational potential energy, because we don't have a spring here. The string is not elastic here, so of course we have gravitational potential energy because there is some height. So this, or the energy that is stored in the system, will be elastic potential energy, which is going to be maximum at this point here. And then what about the velocity? You can say 0 at the point where it stops for a fraction of a second. And then we can say kinetic energy is also 0. And then we can say that the momentum will also be 0 because there is no movement here. And of course, we will have one thing that we've mentioned before, that when it is at maximum here, at this point, this angle, that when, for example, when it is at equilibrium, the angle theta is going to be maximum as well. When it is at equilibrium position, of course, all this is going to be 0, and of course all this are going to be maximum right here. Okay, but one thing that we haven't mentioned, you might say, for the mass spring system, it is very important. If I take you back, for example, let's say here's the mass spring system, and if this is at equilibrium here, let's say after the mass was released here, it is starting, or it starts to go back, yeah, it starts to oscillate back and forth here. We said at equilibrium position or point here, the restoring force is 0. Yes, the acceleration is 0. The elastic potential energy is 0. Okay, what else were 0 as well? Just remember these were 0. Yeah, if these are 0, then how come that the object passes the equilibrium position with a maximum velocity? Have you ever wondered why? Like, why it doesn't stop when it passes through the equilibrium if the force is 0? Have you ever wondered why? Oh, okay. Do you remember Newton's first law of motion? Right? Because of the inertia, or because of the, let's say, momentum of the object, or inertia of the object, you can say, the object is moving, for example, it speeds up, like more and more. At this point here is at maximum speed, so of course, it doesn't stop. In order to be able to stop, it needs a force. So it starts, or it tends to continue moving on the same path as it was before, just like the first law, or you can say using the first law of Newton's first law of motion. An object that is moving will continue to move. An object at rest will stay at rest until an external force acting on the object. So going back to the pendulum here, this is called bob, which is basically the mass. This is the string. All right, and this is, of course, the angle that is, let's say, that is displaced from the equilibrium position here. You can call it theta here. Now, you can either take this side or the other direction side here. Watch this. If I draw some components here, or what is the restoring force in here? We said that displacement here is going to be maximum. You do know that, yeah? So, of course, now there is a tension, or there's a force that is in the string. We call this one tension force, yeah? Or sometimes you can use FT, tension force, that is also fine, or tension itself is a name of the force. But then on the other side here, you can say there is, remember, there is gravitational force. If this is the mass, it's going to be mg, yeah? That is the weight of the object. This mg is going to be analyzed into two components. One of them, for this, that is basically, let me erase this a little so that you can see here. All right, so this mass will be analyzed to two components. So if that is mg, this is going to be, this is going to be, no, okay, let's redraw this. So this is, if that is the case, right, if this is tension, the other side, if this is the mass mg, this mass will be analyzed to two components. One of them is going to be mg cosine theta, okay, cosine theta. You can call this one Fy, yeah? One of them, on Fy, of course, we have F tension, right? Or tension, which is equal to what? Equal to mg cosine theta. Or you can say Fy equal to Ft minus mg, which is equal to 0 because there's no motion or no movement on y direction. So these two are equal in magnitude, but opposite in direction. And of course, we have another component, which is going to be this component right here. Let me use a different color. And of course we have this component in here, which of course there is this, or if that is the angle, this side is going to be mg. If this is cosine, the other side is going to be mg sine theta here. So this mg sine theta, of course, that is the x component, yeah? It is what is bringing this mass back to the equilibrium position. So we can say the restoring force in pendulum is equal to mg times sine of the angle theta. Remember, this mg is basically the weight of the mass, and this is the angle which this string is making with the, let's say, with the horizontal, with the vertical line here, or with the equilibrium position, or from the equilibrium position would be even better to use. Okay, so remember this. The bigger the angle, of course, the bigger the restoring force, you can say, in this case. But what happens at this point here? If at this point here the angle, remember, is equal to 0. So at a point here, we can say that the restoring force will equal to 0. Why? Because we have mg sine theta, correct? And of course, the theta at this point is 0. So of course, mg times 0, you will get a 0 force or 0 Newton. So at this point here, at the equilibrium position, the restoring force will be 0. Okay, so take a look here. The two forces acting on the object are the tension, right, of the string which pulls the bobs upward, you can see. If that is, let's use blue. All right. So once again, this is one of the forces which is pulling the bob upward. And of course, there is another force which is acting on the same direction, but same axis, opposite direction. So these two will cancel one another out. And of course, we'll have mg sine theta. That will be on x-axis. This force is what is bringing the bob towards the, or to the equilibrium, and that is what is called the restoring force. So remember this, and y direction, the two forces will cancel one another out. We have another force that is left on x-axis, which is mg sine theta, and of course this force brings the bob to the equilibrium position. So remember this fg, on x-axis mg sine theta, this is what is called the restoring force in pendulums. Note that the restoring force is 0 at the equilibrium. Why? Because theta, or the angle, is 0 at this point here. So based on this, what does the restoring force on a pendulum depends on? Remember, look at the equation, yeah? The restoring force depends on what? Okay? The restoring force, by the way, the restoring force, this one has to be mg, okay? So make it mg here. So the restoring force, it depends on the mass of the object, and also depends on what? Depends on the angle, not the gravitational, because gravitational is constant. So we can say the mass of the bob, and also depends on the angle, which is, let's say, that is moved or displaced from the equilibrium. So the mass of the bob and the angle of the displacement as well. And of course, this g, that'll be if it is on the Earth, so g is constant, yeah? But of course, if it is on a different planet, we would have, we were saying if we're trying to do this on different planets, we would say that it depends on the gravitational acceleration as well. But as long as it is on the Earth, then we can say the restoring force depends on the mass of the bob, and also the angle which is moved or displaced from the equilibrium. Okay, and then perhaps the last few things for this session as well. Remember, for small angles, the pendulum's motion is considered simple harmonic motion. Remember, do you see that when the motion of, we said the motion of the pendulum is periodic, so it moves back and forth, yeah? Do you know that when the angle is very small, let's say in terms of 15 degrees here, then 15 degrees is very small. So we can say 15, or sine 15 degrees is always equal to 15, let's say, equal to, let's say, 15 degrees in this case, or 15 radians in general. So of course we can say the pendulum's motion is an excellent approximation of simple harmonic motion. So when can we consider the motion of a pendulum to be simple harmonic motion? We can say this, yeah? When the angle for example, is small enough, or when the angle is smaller than 15, let's say 15 degrees, then of course we can say that the motion of this pendulum is simple harmonic motion. So once again, remember, not even equal to, it has to be smaller than 15. If this angle is smaller than 15 degrees, then this motion can be considered as simple harmonic motion. Gravitational potential energy increases, of course, as the pendulum's displacement increases. So of course we've mentioned this one earlier. Let's say we have this pendulum that is swinging back and forth, okay? So we do know that this bob is moving back and forth. Yeah? What do you think will happen if the bob is here? At another point, the bob is here. So can we say that the bigger the displacement here, okay? What do you think will happen when the displacement gets bigger and bigger and bigger? So of course, this height will increase more and more, yeah? So the bigger the height, the more the gravitational potential energy, okay? Once again, the more the gravitational potential energy. So we can say, but at this point here, all the GPE will be converted to kinetic energy. So at this point, the energy will be solely kinetic. The energy here is solely gravitational potential energy. These two are changing always. The kinetic energy and potential energy of the pendulum is always changing, but one thing that doesn't change is the mechanical energy of the system, and this was one of the WSAT questions, by the way. You can see here, GPE, gravitational potential energy, at this point here is maximum, yeah? Max. As it moves downward, of course, approaches the equilibrium, it gets less and less and less, so this GPE will convert to kinetic energy. Kinetic energy starts to increase. Let's clean up this. So at a point here, we have maximum gravitational potential energy, max. Here, kinetic energy is max, okay? At a point here, we have both kinetic and potential energy here, or gravitational potential energy. But here, it's solely potential, gravitational potential. Here, solely kinetic energy. So these are changing always, yeah? But one thing that never changes is, which is the mechanical energy. Mechanical energy would be the total kinetic energy plus the gravitational potential energy of the system, which is always constant, assuming there is no friction or air resistance, or if we have an ideal system, let's say. Okay, so the mechanical energy of the simple pendulum is conserved in an ideal or frictionless system. However, the spring's potential energy is elastic. If we have a spring, that would be elastic, while the pendulum's potential energy is gravitational. Remember, for the spring that we had, because the spring is stretched, so the type of the energy there, it is elastic potential energy. Yeah, but this one here, of course, because it is moving, so there is a height above the ground, so we have gravitational potential energy. We define the gravitational potential energy of the pendulum to be 0 at the equilibrium position. That is, like for example, just to make calculations easier, we consider that the equilibrium position, the GP is 0. Okay, at the lowest point, you can say, of the swing. Gravitational potential energy is maximum at maximum displacement from the equilibrium. So we have two questions here. We have question 3 in chapter review says, what is the type of the energy of a pendulum bob before it is released? Before it is released, let's say you just pull it all the way up. So the type of the energy is gravitational potential energy, correct? Once you let it go, this GPE is going to decrease. All of it will convert to kinetic energy at equilibrium. Then it starts to decrease again until all becomes gravitational potential energy. Then it swings back and forth, yeah? So this energy will change between gravitational and kinetic energy. Okay, so what is the second part? It says, how does the energy of the bob change as it swings through one full cycle of motion? So before we release the bob, okay, let me draw this one. Perhaps it would help to understand this better. Here's the bob before we release. Here's the equilibrium position. And let's say this is the other end. So here's the swinging path. At this point here, before we let it go, it is all gravitational potential energy. As we let it go, it decreases, kinetic energy increase. At a point here, it is solely kinetic energy. Then, after it passes through the equilibrium, kinetic decreases, gravitational potential energy increase until gravitational potential energy becomes maximum here and kinetic becomes 0 here. So this would be max, kinetic would be 0. Here kinetic is 0. Again, this is max GPE. And then here kinetic energy is max, but GPE, gravitational potential energy, is 0. So this is how the energy is exchanging between these two. But remember, the mechanical energy will always be conserved. So at equilibrium, you can see here, GPE decreases to 0, kinetic is maximum. After it passes through the equilibrium towards the maximum displacement, kinetic energy decreases to 0, GPE increases to maximum, and then the cycle repeats, keeps moving back and forth. Question 5 says, in a simple pendulum, the weight of the bob can be divided into two components, one tangent to the bob's direction of the motion, and then the other perpendicular to the bob's direction of motion. Which of these is the restoring force? Explain why. And of course, the one that is perpendicular to the, let's say, the component tangent to the bob's direction of motion, mg sine theta, because it is, or this one always brings the bob back to the the mass back to the equilibrium position. So remember, we said for pendulum, perhaps I can draw it here. We said there are two components, yes? One of them, if this is tangent, which is upward, there is mg cosine theta, which is downward. Yeah, these two will cancel out. So one thing that always brings the bob back to the equilibrium, that is what? That is mg sine theta. Yeah? Okay, so this would be in this case, or this is the one that brings the object back to the equilibrium position. And that is the end for this session. Next time we'll continue talking about this, and of course we'll solve questions. And until then, keep practicing, and I'll see you next time. Thank you.